Hello everyone, welcome to this course on Software Defined Radio Hands-on for Communication Systems Design. I am Professor Suraj Srivastav from the Department of Electrical Engineering at IIT Jodhpur. And in the last lecture, toward the end, we had seen an introduction to MATLAB Simulink and SDR environment. And today we will explore it further. So what we had seen in the last lecture, generally the message signal is denoted by MT. So the MT is the message signal which we have to transmit. For example, for the analog case, it can be a speech signal or audio signal. These are the analog signals, and for them we will be using analog modulations. Or for the case of digital communication, we will have the message signal in the form of bits which will be transmitting using a digital communication system. So in general, the MT is being used for message signal to be transmitted, and this message signal MT is given to the MATLAB Simulink model running on the host computer. Now finally, the ST is the final modulated waveform which is passband and real valued in nature. So the role of SDR is to generate the final passband waveform ST corresponding to a particular modulation schemes. For example, if we consider the speech signal or audio signal, which is the analog modulating signal, so in this case the ST is represented using a expression like AC into 1 plus Ka MT multiplied by cosine 2 pi FCT. So right now it is not very important to explore this expression. I am just giving you some examples. In the subsequent lectures, we will explore these expressions. So this is for amplitude modulation, AM. And if this is a digital communication systems like BPSK, then this ST will become plus or minus AC cosine 2 pi FCT. So in this case, the AC represents the carrier amplitude and MT represents the message signal we already discussed. The other important quantity is the carrier frequency FC. So this ST, which is the output of transmit SDR, is the final waveform, whether it is AM or it is BPSK for the case of digital communication, and this is a real valued waveform. So this is the waveform which the transmit SDR generates corresponding to the message signal MT and for a particular modulation scheme like amplitude modulation or BPSK, and this is the waveform which is transmitted over the air by SDR. So right now these expressions are not very important, but the important point here is to note that these kind of expressions which you see in the regular textbook, for AM it is AC into 1 plus K MT cosine 2 pi FCT, and for BPSK it is plus or minus 1 AC cosine 2 pi FCT for binary bit 1 and 0 respectively. So these are the expressions corresponding to the real valued passband signal which the transmit SDR has to generate. Now let us try to understand what is the role of MATLAB Simulink model running on the host computer. Now this we briefly discussed in the last lecture, but now we will explore it further. The role of MATLAB Simulink model running on the host computer is to generate an equivalent complex valued baseband representation of the signal ST. Okay. So for example, if you look at the previous slide where I mentioned the passband representation of amplitude modulation as AC into 1 plus K MT and the passband representation of BPSK as plus or minus AC cosine 2 pi FCT. So their corresponding S tilde T will be AC into 1 plus K MT. This is for AM, and similarly this S tilde T for BPSK will become simply plus or minus AC in the bit duration TB. Okay. So right now we are not focusing too much on these things. These will be explored systematically in the subsequent lectures, but I am just giving you an example that this is what is the role of the Simulink. The Simulink model generates the corresponding equivalent complex valued baseband signal corresponding to this ST. Okay. And although it is not very clear in this case, that S tilde t is a complex valued signal, but in general you will see for many other modulation schemes like frequency modulation or the quadrature amplitude phase shift keying QPSK, this S tilde t, the signal generated by the MATLAB Simulink, the complex equivalent baseband signal, will be complex valued. So this is what I mentioned here very briefly. MATLAB Simulink model running on the host computer generates an equivalent complex valued baseband signal corresponding to ST, and this S tilde t is also called complex envelope of ST. And as you can see that in the previous slide, S tilde t depends on the message signal MT and also what is the modulation scheme. For example, S tilde t for AM is this, which relates to the message signal in a particular way, but for the S tilde t for the digital signal is this, which relates to the binary signal 0 or 1. So the important point here is that this S tilde t depends on the message signal MT and the modulation scheme. And this is the S tilde t which is sent to the transmit SDR via Ethernet or USB connection. And the role of transmit SDR is to convert this S tilde t into the final waveform ST, which for the AM is this and for BPSK modulation is this. Now, I would like to emphasize here that this complex baseband equivalent of a real passband signal or complex envelope of a real passband signal is not a new concept. It's already taught to many of you at the undergraduate level, but it may not have been emphasized enough, mainly due to the fact that during our undergraduate courses, the focus is more on generating the passband waveform ST and visualizing it with respect to time and frequency. So that is why we don't enough emphasize the equivalent complex baseband signal or the complex envelope, but it's already taught at the undergraduate level at the very beginning. But here you will realize that this S tilde t is a very important quantity and this holds the key for SDR based implementation. And you will see that not just for SDR based implementation, for all our academic research, theoretical analysis and deriving the performance bounds, this S tilde t plays a very important role, because this S tilde t has all the information present in the message signal and also it has the information of the modulation scheme. So that is why it's very important, and we will explore this S tilde t further subsequently for the SDR based implementation. So now if I look at the complete picture, so the message signal MT is given to the MATLAB Simulink model which is running on the host computer. This Simulink model will generate the equivalent complex baseband representation of ST. This will be given to the transmit SDR using the Ethernet cable or the USB cable, and then the role of transmit SDR is to generate ST from this S tilde t, and this final waveform ST will be transmitted over the air via SDR. Similarly, let us look at the receiver side. What receiver will do? So first, this transmit signal ST will be propagated through the wireless channel and then it will be received at the receiver. RT will be a distorted and noisy version of the signal ST. So this RT is again a real valued passband signal, and then the role of SDR is to convert this real valued passband signal into an equivalent complex envelope. So this is the role of the receive SDR. So RX SDR generates R tilde t. R tilde t represents the complex envelope of RT. So R tilde t is generated by the RX SDR, and this R tilde t is sent to the MATLAB Simulink model running on the receiver side host computer. And this Simulink model running at the receiver side will extract the message signal or recover the message signal M hat t from R tilde t. So this is the complete picture which we have for SDR based implementation. So this is the overall design philosophy for prototyping a communication system. Once again, I will mention here that SDR, the software defined radios, are not the end product of a communication system. They are used to prototype a communication system in the initial phase. And finally, once a system is validated through SDR, it has to go in the form of an application specific integrated circuit, which we call as ASIC, in the form of a product. So this is the design philosophy of prototyping a complete end-to-end communication system. Now let us look at some of the key observations which will further emphasize the role of this equivalent complex baseband signal S tilde t and R tilde t. So let us explore this thing systematically. What are our key observations? So first thing, what we see that the baseband Tx and Rx signal processing part is performed in MATLAB Simulink models which are running on the host computer. So these blocks, MATLAB Simulink block at the transmitter and MATLAB Simulink block running on the host computer of the receiver side, they perform the fundamental signal processing operations. For example, the channel coding, decoding at the receiver. Similarly, the modulation at the transmitter and the demodulation at the receiver. Generating the complex waveforms S tilde t using the pulse shapes, right. So all these operations are done in this MATLAB Simulink model. All the signal processing related, baseband signal processing related operations are done in this MATLAB and Simulink models which run on the host computer. And this signal processing which we done in the Simulink model, they depend on the modulation scheme. So the processing which we do here in the MATLAB Simulink will depend on whether it is AM, FM or BPSK, QPSK. For different modulation schemes, the Simulink models will be different. Whereas the RF domain processing is performed via SDR. So that means what is exactly the RF domain processing? So converting the EM signal, converting this S tilde t into the EM signal is the RF processing. So this RF domain processing is done by the SDR. So SDR will basically generate ST from this S tilde t. And this operation, RF domain processing performed via SDRs, is highly independent of the modulation scheme. So this also we'll realize when we'll go to the expression, but in very short I'll explain you how do you get this ST from S tilde t. So ST is basically real part of S tilde t into a complex carrier e raised to the power j times of 2 pi fct. So essentially this is the operation which is performed by the Tx SDR. And you see that this operation does not depend on the modulation scheme. So irrespective of whether S tilde t is amplitude modulated, frequency modulated or any digital modulation, the generation of ST from S tilde t is fairly standard. This is the expression. We'll go through this expression once again when we will establish the relationship between ST and S tilde t. But this is just to explain that the RF processing done at the Tx SDR is independent of the modulation scheme. So the key observation here is that the complex envelope S tilde t generated via MATLAB or Simulink model depends on the modulation scheme that we have seen, and it contains the message signal MT. Whereas converting the S tilde t to ST, essentially converting the baseband signal to the electromagnetic signal ST via Tx SDR is a very standard operation, and it is independent of the modulation scheme and the message signal MT. So once you have obtained this S tilde t, the RF processing does not depend on what is the message signal MT contained in S tilde t or what is the modulation scheme used to generate S tilde t. So this is what we mentioned, converting S tilde t to ST via Tx SDR is a very standard process, and it is independent of the modulation scheme and the message signal MT. Now similarly at the receiver side, converting the received signal RT, which is the real passband signal, to R tilde t, which is the complex envelope of RT via Rx SDR is again a very standard process. So I'll not explain it right now, but this conversion is also a very standard process and it does not depend on the modulation scheme. So this is also a very standard process. It does not depend on the modulation scheme. Whereas recovering the message signal M hat t from this complex equivalent signal R tilde t via MATLAB Simulink depends on the modulation scheme. And this we already explained that getting the R tilde t, getting the message signal M hat t back from R tilde t will require the knowledge of the modulation scheme, channel coding scheme and pulse shape, etc. So all the signal processing part which recovers the message signal m hat t from the complex equivalent baseband signal of the received signal r tilde t, this depends on the modulation scheme as shown here, right. So the recovering the message signal m hat t from r tilde t via MATLAB Simulink model depends on the modulation scheme. So if you look at closely, if we divide these two operations by this dotted line, the left side of this dotted line is the baseband signal processing part, which is the brain of a communication system, because the modulation, demodulation, channel coding, decoding, pulse shaping, match filtering, all these things happen in the baseband signal processing in the MATLAB Simulink running on the host computer. Whereas if you look at the right side of this dotted line, this is just the RF processing. This is just like a carrier. The role of carrier is to carry this S tilde t over the radio waves and recover this R tilde t or get this R tilde t back from the EM waves. So this is the role of the right side, the RF processing of this block. So now a very important question arises here. Can we design both TX and RX baseband signal processing part, which is on the left side of this dotted line, without connecting with the SDRs? Can we design both TX and RX baseband signal processing part, which is on the left side of this dotted line, without connecting through the SDRs? Especially this is required during the initial phase of prototyping, or let's say when you don't have the TX and RX SDRs and you are waiting for these TX RX SDR. Can we design the left side? Can we design the baseband signal processing part without the TX and RX SDRs? To answer this question, let us systematically go through this. Now we note that to generate this S tilde t, we don't need TX SDR, right? Because the S tilde t is generated using the MATLAB Simulink model, which is running on your host computer. So to generate this S tilde t, we don't need the TX SDR. However, to obtain this R tilde t, we need both TX SDR and RX SDRs, right? Because this S tilde t will be given to the TX SDR, it will generate ST, then it will, this signal ST will be propagated over the wireless environment, received at the receiver side antenna, and then receive SDR will convert this RT into R tilde t. So to get this R tilde t from the real wireless environment, you have to use TX SDR and RX SDR. Now it's clear that to generate S tilde t, we don't need TX SDR, but to get R tilde t, we need both TX and RX SDRs. So now I'll rephrase this question again, and I will ask the same question in a different way. Can we generate R tilde t without using TX SDR and RX SDRs? Because if you can generate R tilde t without using TX SDR and RX SDR, that means you can do the baseband signal processing part without TX SDR and RX SDR in the MATLAB Simulink. And fortunately, the answer is yes, we can generate R tilde t without using the TX and RX SDRs. And how do we do this? So here comes the concept of wireless channel modeling. So if we model the TX SDR, or if we model the behavior of TX SDR, RX SDR and this wireless channel by a complex baseband wireless channel H tilde t, right? So if we model this whole thing, this whole block, dotted block, using a wireless channel model H tilde t, then directly you can generate R tilde t using this model H tilde t. So after all, this R tilde t will be a distorted and noisy version of S tilde t. Very similar way which I mentioned, that this RT, the passband signal RT, will be a distorted and noisy version of ST. So in a very similar manner, this S tilde t or R tilde t will be the distorted and noisy version of this S tilde t. And if we can generate this behavior of TX SDR, wireless channel and RX SDR, if we can model the behavior using a complex equivalent baseband channel H tilde t, then you can directly get R tilde t from S tilde t. So, answer is yes. Using a suitable model for TX SDR, wireless channel and RX SDR, one can obtain R tilde T without actually transmitting S tilde T through the SDR. This is where the wireless channel modeling comes into picture. Hence, a communication system design or prototyping phase can be realized in two phases. In phase 1, you can design and test the baseband signal processing part through simulation. That means generating R tilde T directly from S tilde T using a channel model. And there are many well established wireless channel models available in the literature, such as the simplest one is the additive white Gaussian noise channel, and then there are wireless fading channel models. So, there are many existing well established wireless channel models which one can use to obtain R tilde T from S tilde T, and one can completely work in the simulation to design the baseband signal processing algorithms. And once you are ready with the baseband signal models, the Simulink models, then you can move to phase 2, where you can connect your MATLAB Simulink models with the actual SDRs for over the air transmission to obtain this R tilde T. And once you get the R tilde T, then again you can feed the same R tilde T to the receiver side Simulink model to recover the message signal M hat T. So, this is what is summarized here. If you want to work in the simulated environment, then you can generate the S tilde T. From there, you can directly generate R tilde T without transmitting it using the channel models. And then again, you can run the baseband signal processing algorithms of the receiver side to recover the message signal M hat T. But to complete the prototyping phase, you have to connect to the SDRs and then you have to complete the experiment. And therefore, as we discussed, channel modeling and channel estimation is very important for wireless communication system. First thing is to model the wireless channel so that you can work in a simulated environment and develop the signal processing algorithms, and also to compensate the effect of wireless channel. During this course, we will mainly focus on the additive white Gaussian noise channel, which in short we call it as AWGN channel. So, during this course, we will focus on the additive white Gaussian noise channel, which is the simplest model for the channel, the wireless channel, but it holds for most of the lab environment. So, this is a channel model which we will mostly focusing during this course. But of course, once you understand the principle, you can extend this with the other wireless channel models also. Then you have to do the channel estimation and equalization. But we will further consider the hardware impairments due to the local oscillators used in these SDRs. So, generally the local oscillators which converts the baseband signal. So, the TX SDR and RX SDRs have the local oscillators, and these oscillators converts the baseband signal to the RF signal. These are generally imperfect in nature. So, we will simulate the behavior of these local oscillators in the form of hardware impairments, which actually lead to the frequency and phase offset between the transmit and RX SDR. So, we will consider this during our course, and for the channel models, we will mostly focus on the additive white Gaussian noise channel models. So, now let us see the summary of this discussion. So, as we discussed, SDR based implementation of communication system enables a modular design framework, because the baseband communication engineer and RF engineer can work independently during the initial phase. The baseband communication engineers can mostly focus on designing the signal processing algorithms and test them on the various baseband channel models, whereas RF engineers can focus on the RF processing, basically how efficiently to convert the baseband signal to the electromagnetic waves. So, you see now there is a well defined separation or well defined task for the baseband communication engineers and the RF engineers. At the initial phase of the prototyping, they can work independently, and once they have their own design, then they can connect through the baseband signal with the RF processing and perform the complete end-to-end experiment. And I would also like to highlight here one very important point, that most of the academic research, IEEE papers or any other similar academic repositories focus on designing the baseband signal processing techniques, followed by their performance evaluation through simulations, and also we work extensively on deriving the theoretical analysis performance bounds using the statistical channel models. And all these three things For all these three things, we don't need SDRs. We don't need software defined radio. You can work all these things in the simulated environment. So these three things, designing baseband signal processing techniques, performance evaluation through the simulations, and deriving the theoretical analysis and performance bounds using the statistical channel model, can be performed without actually bringing the RF hardware or software defined radios into picture. So that means the assumption here is that we assume the RF hardware or SDRs to be ideal, and we consider them only as a carrier. Okay. And one last thing is that most of the innovations in the communication systems design happen at the baseband level, and that is why we have to very clearly understand this S tilde T. This S tilde T is the complex baseband signal which is generated using the MATLAB Simulink, and we have to, for all the modulation schemes and for all the SDR based experiments, one has to clearly understand what is the S tilde T corresponding to the final modulated waveform ST. So the role of this S tilde T is that by working on the simulated environment, most of the signal processing techniques can be done, and most of the innovations also in the communication systems happen at the baseband level. Thank you everyone. So let's conclude this module, and in the next module we will start with the basics of digital signal processing through Simulink. Thank you.